All right. Hello, everybody. Today we are talking about 6.4 work and power. Okay. I'm just going to pull that up here. Great. Okay. So today we are doing topic 6.4. This is focusing on power in particular. In the last few topics, we have been learning about different types of energy. So kinetic energy and potential energy. So we've been talking about those two types of energy and how those two combine to form mechanical energy, or the total energy in a system. Okay, work is equal to force times distance. Of course, the force needs to be in the same direction as the displacement. So in some of those questions, we might need to do a little bit of trigonometry to help us find the force that is in the right direction, or in the same direction as the displacement. Okay, today we're going to talk about power. And if we look at the top right corner of our screen here, we'll see the formula for power is equal to work done over the time that has elapsed. Okay, so in general, in our everyday lives, the word power is not necessarily, it's kind of a generic term. And it's most often associated with electricity in our everyday lives. But in physics, we have a different definition for power. Okay, so power is the rate at which work is done. So in other words, power measures how quickly energy is being used. So if we look at the bottom of our screen here, we will see the formula for power, which you will find on your formula sheet. Okay, so power is equal to work over time. Okay, and also on your formula sheet, you will notice, and you should remember, that work is equal to the change in energy of the system. Okay, so we can substitute in change of energy for work here, and we can calculate power by finding the change in energy divided by the time here. Okay, note that the units for power are watts, so that's going to be a joule per second. The units for work or change in energy is in joules, and time will of course be in seconds. I'll turn down for watt. Okay, James Watt, just a little bit of background on him. He was really concerned with trying to improve the efficiency of machines that people were using back when he was alive. And due to his accomplishments and his contributions to the efficiency of machines and improving that, the scientific community named the units for power after James Watt. So the units for power are watts. So that is life goals right there. Have units named after you. Okay, so just a little bit more talk about power. So this is measured in watts. Again, this is joules per second for the units. And just to give you kind of an example of what a watt looks like. So a 60 watt light bulb uses 60 joules of energy every second. Okay, 60 watt light bulbs are pretty standard, what you will find around your house. So even in the few minutes that we've been recording this video, probably used a couple thousand joules of energy. Okay, so let's get into the examples here. So I'm just gonna pin this video here and make it big so you guys can see that. All right, so here is our example one. So we have a 150 watt light bulb is left on for 2.5 hours. So we're trying to find how much electricity or energy was used. Okay, so like we've been doing, let's just write down what we know our variables are. So 150 watts, that's power. We have a time of 2.5 hours, and we're looking for how much electricity or energy has been used. So what is the change in energy in the system? Okay, so from our formula sheets, we know that power is equal to work over time. Work is equal to change in energy. So we're just going to substitute that in right there. So we can rewrite that as power is equal to change in energy over time. The power. Okay, we have power, we have time, and we're looking for the change in energy. But before we get going there, let's change our units of time into seconds. Okay, so we're in hours. We're going to multiply by 60 minutes for 1 hour. And we're going to multiply that by 60 seconds by 1 minute. Okay, if we do that, our hour units will cancel. Our minute units will also cancel, and we will be left with seconds here. So 2.5 multiplied by 60 multiplied by 60 will give us an answer of 9,000 seconds. Okay, so now that we are in the right units, we can substitute in these values after we do a little bit of manipulating. Okay, so power from up here is equal to change in energy over time. We're looking for the change in energy, so multiply both sides by T. That will cancel. Now we're left with change in energy is equal to the power multiplied by the time. So now we can just substitute this in. Change in energy is equal to 150 watts multiplied by 9,000 seconds. We'll punch that into our calculator. Rounded with sig digs, we will get a value of 1.4 times 10 to the 6 joules. All right. That is question 1. Okay, so we're just going to talk about a little bit more formula substitution here. So in some questions, you're going to be, there's the velocity within the questions are going to be at a constant velocity. Now, in reference to our last unit, remember, if something is moving at a constant velocity, the F net is equal to 0, right? So just keep that in mind. Yeah, so power is equal to work over time. So we see this on our formula sheet. And we also know, so I'm just gonna, so we'll start over here. So power is equal to work over time. Okay, we know that work is equal to the force times distance. So we can substitute that in here. So we get power is equal to force times distance over time. Now, I don't know if this looks familiar for you guys. We have distance over time. So remember, velocity is equal to distance over time. So we can substitute this into here now. So now we get power is equal to the force times velocity. Okay, and that's how we get over here as well. Just wanted to show you that in a stepwise manner. This is not on your formula sheet. So you will need to know how to get from power is equal to work over time to power is equal to force times velocity. Okay. So let's just keep cruising through the examples. So we have a 200 watt motor. So that is power. Anytime that you see watts, you should think power, okay? This is being used to lift shingles at a constant velocity to the top of a roof, okay? So constant velocity, remember F net is equal to 0. Okay, so we know our power, we know our mass is 28 kilograms, and we're looking for the velocity. Okay, so we have power and mass. So if we look at our formula sheet, we might not be in too much luck, but that's all right because we know how to derive formulas now. Okay, so power is equal to work over time. This one is from our formula sheet. Remember, work is equal to force times distance. So we can substitute that in for work. So power is equal to force times distance over time. Distance over time is equal to velocity. So we can substitute that in here. So then we get power is equal to the force times velocity. Sorry, power. Power is equal to force times velocity. Okay, so in this case, we are looking for the velocity. So let's divide both sides by V, or by force. Sorry, my cat is trying to come up here and he's kind of distracting. So my apologies there. So anyways, we're dividing by F to isolate for V. So divide by F on both sides, these F's cancel. So we'll be left with velocity is equal to power over force. So we know power, but we don't know force yet. So that's okay, because think of our forces unit. We know that the force of gravity, or just like the force that this pack of shingles will exert, is equal to the mass times the acceleration due to gravity. So Fg is equal to 28 kilograms times 9.81 meters per second squared. We do that. Fg is equal to 274.68 newtons. So that force Fg is the same as F there. Okay, so now now that we have power and we have our force of gravity, sorry. So now we have our power and our force of gravity, we can substitute our values here to find our velocity. So power is 200 watts divided by the force, which is 274.68 newtons. Punch that into our calculator, we'll get a value of 0.73 meters per second. Okay. We'll continue, and only one practice problem to go. All right, so example 3. The power output of a car is usually measured in the non-metric unit horsepower. Okay, you guys might have seen this on like car commercials before and stuff like that. Or if you guys are talking about how much horsepower a car has, okay, that is a non-metric unit. Leave it up to the Americans to still use non-metric units. Okay, so a car that we are looking at has an engine rated at 120 horsepower, which has the same power as 8.95 times 10 to the 4 watts. Power is equal to 8.95 times 10 to the 4 watts. If the car is moving against air resistance, so remember the force of friction is opposing all of our motion. So in this particular case, it's air resistance. So I'm just going to write force of friction instead, because that is what's opposing our motion. So the force of friction is equal to 4.00 times 10 to the 3 newtons. We're driving at a constant velocity, so we should automatically think F net is equal to 0. Okay, that is going to be important to solving this problem. And we are asking for the velocity. Okay, just because our F net is equal to 0 does not mean that we are not moving. We're just moving at a constant velocity. Okay, so we know the power, we know the force of friction. So let's just draw an image for this car. So to make it go forward, it has an applied force. Okay, and it is being opposed by the force of friction. Because we're on a horizontal plane, we're not like gaining any elevation. Fn, the normal force, is going to equal to the force of gravity, so we can just exclude that from here. Okay, so now if we do a Fnet formula showing all of the forces present in our free body diagram, we will get Fnet is equal to the force applied plus the force of friction. So Fnet is equal to 0, so we can just get that, we can just get rid of that term. And let's isolate for our applied force. So we'll subtract force of friction from both sides. These will cancel. We're left with negative force of friction is equal to the force applied. Okay. So we know from here that the force of friction is 4.00 times 10 to the 3 newtons. So we can just substitute that in. So I'm assuming that this way is positive and to the left is negative. Okay, so the force of friction is opposing the motion, so that is going to be a negative value. So I'm going to have negative 4.00 times 10 to the 3 newtons is equal to the force applied. Just simplifying our negative signs there, we will get our applied force is 4.00 times 10 to the 3 newtons. Okay, if you are able to make the connection that the applied force here is going to be equal to the force of friction there, you don't need to do this step, but I just wanted to show you guys so you know where we're, just how we got to this point, how we knew that the applied force was 4,000 newtons. All right, so now we know the force of the car is 4,000 newtons. We know the power. Oh, there we go. We know the power here, okay, and we're looking for the velocity. So let's start from the top again. So power is equal to work over time. On your formula sheet, work is equal to force times distance. So power is equal to force times distance over time. Distance over time is equal to velocity. So power is equal to the force multiplied by the velocity. That's what we're looking for, right? We're looking for the velocity. So let's divide both sides by the force. Okay, velocity is equal to power divided by the force. Okay, so now we can just substitute in our values. So power is 8.95 times 10 to the 4 watts divided by the force applied, which is 4.00 times 10 to the 3 newtons. Okay, and then if we punch that into our calculator, we'll get a final value, velocity with rounded to the correct amount of sig digs, we'll get 22.4 meters per second. All right, so those are the 3 examples for this section. If you need any help with these questions or have any concerns or problems, just send me an email. I'd be more than happy to get you on the right track. Okay. Tomorrow I will be in standby. So if anybody needs any help with these, or if they want me to re-explain any of the practice problems, I will be available for that. All right. Just due to popular demand, we wanted the lessons in advance. So here you go. All right. I hope this helps. And I hope you all have an enjoyable rest of your day. Take care.